not even that cold.
All right, let's start with a little review. Quick reaction series, and then let's practice the mechanism for that Burke reduction. I'll give you a few minutes.
So just the product for the first one, right?
Yes, yeah.
It's.
Step one. We do make stereocentric so that we keep track of the fact that it's our first steps in case it matters to the next step. It doesn't. Because next step is what?
Take away the bogey.
Which we call what? What type of reaction is that? Oh, come on. Go to our first ones. The other one.
Elimination.
Yes. The opposite of addition. What's the advantage of using TBOK instead of a different base? Instead of just using hydroxide?
It's circling.
Which makes it, which has what effect? That is the advantage, but what does it do?
It doesn't have like side reaction.
What would the side reaction be if we use AOH?
That's what they would. The hydrogen would like, or hydrogen sort of
It's a better nucleophile, it's not steroid engineered, so we get some substitution. We do that, so in that case, we would wind up with OH here, we get some of the elimination product. But using TBOK is a way to make sure we only get the elimination products. So TBOK is a sterically engineered base is almost always a better option if you want elimination, unless you need this 8-step rocket, because this only gives us the Hoffman. In this case, we don't have a choice. We only get them. There's no 8-step versus Hoffman, but we might as well use the sterically engineered base and get 100% elimination products or within sync base. Good. Nice little review there. And how's the mechanism going? You started on that one? Okay, give it a go.
Well, there's too much stuff. The NA is just out of balance.
No. Because it's not Na plus.
Oh, okay.
It's sodium metal.
Yeah.
So the fact that it's sodium metal tells us it's an electron donor.
Okay.
And this is one where you might want to draw the product first, so that you know where to draw your electrons attacking and moving, because for this Birch reaction, this Birch reduction, we know that having different substituents changes which carbons get reduced, which ones keep double bond, right?
Yeah, like this one's gonna have the.
Good. Why?
Because the methyl groups are different to these substitution. That's not the right word.
Yeah, the methyl groups are electron donating.
Yes.
And that means, and this is a reduction, right? Which means we're adding electrons to carbons. We're not going to add electrons to a carbon that has an electron donating group attached to it, because there's already extra electron density there.
Right.
So forcing more electrons onto it is not a
Maybe you just stop letting me make circles and just draw it on your own. Always split. If this was a question of test, you know how like our rounds we learned before we had two bromides together and then we should split it in. Should we show that? In this case,
No, because sodium as a metal already is a free radical.
okay.
Because it only has one electron in that outermost layer. Good question though. If it's something that's already, that's stable-ish, and then we need to turn it into free radicals, we'd do that, but the fact that we're starting with sodium metal, that tells us we're already starting with the radical. Well, if we get this first step going. What's next? Yeah.
The OH. Takes the negative attacks the hydrogen and then the bottom stops.
Okay. There's quick proton transfer.
It's. And then we repeat. And then radical. Well, probably 3 times.
That gives us another carbon ion, which then we just proton transfer again. Really, the trickiest thing about this one is just that first step.
Yeah.
And keeping track of is it single barbed arrow versus double barbed arrow. So for our sodium based steps, we have a single barbed arrow, so we move 1 electron at a time. Everything else is double barbed arrow, so it follows our normal rules.
And when we draw the electron step, should we draw the arrow coming from the negative or from the free radical pair?
For this first one, it's got to be from the negative. No, it's a proton transfer, not a free radical step. So if the free radical attacked the hydrogen, it would actually be taking one of these electrons.
Yeah.
We would have something different that looked like that. And then we'd make another radical, but yes. Because it's more favorable for this radical to react with the sodium. It doesn't do anything yet. We just do the proton transfer. And so it has to go to the, it doesn't matter which side you put the negative and which side you put the radical, it's the negative that gets the proton. All right, we good?
Yeah, because we don't draw H's, we don't have to draw the ones react radicals.
Correct. If we wanted to, you could certainly, there is already a hydrogen on here, you could draw with 2 hydrogens after this.
Right.
So it would look like this now. This one already had a hydrogen attached. So we really had something like that. And so we end with hydrogen, 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 hydrogen.
And when we do the half arrows, those are coming from the dot. We're going.
That's so when we have these the half arrows are when we're only showing a single electron moving at a time. And so that's the only time you'll ever draw an arrow pointing towards another arrow or an arrow pointing towards electrons, because we're grabbing 1 electron from one side and 1 electron from the other to make a new bond that's a pair of electrons.
Oh. But, yeah,
That's better than what I thought it was, like tuna salad. That's early in the morning, it's tuna salad. Then again, I like salmon on my bagels, so it's not all that different.
yeah, I would not be able to do.
All right. So today's new edition, this title of this lecture is one reaction or one mechanism, basically. But it's 5 reactions. Because there's 5 reactions that all basically do the same thing. Just like substitution, you could call substitution like 10 different reactions that if you switch out what the nucleophile is, right? The mechanisms mostly look the same with a few small differences. That's what we're going to do again today. So this reaction is called electrophilic substitution. And it looks a little bit different because, well, one, it's electrophilic. We haven't dealt with much in the way of electrophilic reactions yet. And it's going to look kind of like an addition reaction first. Because if we just let an alkene react with bromine, we know we can do an addition reaction. We wind up dibrominating it. We get this molecule. We can't do that with benzene because the aromaticity is too strong. We're not going to break a pi bond to add bromines to it because that would disrupt the entire aromatic character. And so now, if it happens, this product is no longer aromatic, right?
Right.
Is it anti or is it non-aromatic?
It's not, because it's not fully functioning.
Right. So anti-aromatic is more of a niche case where it meets all the criteria for aromatic except with an odd number or an even number of electron pairs. Non-aromatic is anytime you've got sp3 carbons in the ring. But what we do see that if we add the right catalyst, we can get a different reaction. We don't break our pi bonds. We're actually going to do a substitution reaction. And the substitution reaction is going to look a little bit different, specifically because we're actually going to replace a hydrogen this time. We've never done a substitution. We always had to have a leaving group for a substitution reaction. But because this is an electrophilic substitution, all of our normal rules are kind of flipped. So in this case, hydrogen or proton is going to be a good leaving group because we're going to introduce something that wants to grab some of these electron pairs. These 3 electron pairs that are part of the air that cause the aromatic character are a good target for something that's missing electrons. So something that's missing electrons is going to be attracted to electrons. That makes it electrophilic, right? And in that case, what we're actually going to do is we're going to replace a hydrogen because the hydrogen then just gets lost with the proton. And we do a proton transfer because we're bringing in something that's missing electrons. That's what changes everything. Right, so this, we typically only see this with aromatic situations. If it's not aromatic, we'll usually just see a regular addition reaction. We'll break the pi bond to make sigma bonds. The only reason this works is if it's aromatic. All right, so here's our net reaction. There's 6 of them. I take it back, not 5. We can do this with a bromine. We can do it with a chlorine. We can add a nitro group. And we can add a sulfur group. These other 2 are less reactive, especially this one. These are special class reactions that allows us to add alkanes to benzene rings, but this one in particular has pretty low yield. This one's a little bit better.
Does R have to be any specific?
R is any alkane.
Okay.
That meets our, we'll add the rest of the reactants to show you how we do this.
But basically, this is a way we could add an isopropyl group, we could add a T-butyl group, etc. If we have the right reactants.
So any alkene, I'm gonna say like that meets something.
Let's wait till we get to that reaction. We're going to go through them from left to right because these are the one. This is basically almost from left to right. They go from highest yield on the left to lowest yield on the right. If we look at these two,
Well, I was gonna say like I can't.
it doesn't. And we'll talk about why when we get there in a minute. All right, so let's start with bromine. Bromine's always one of our go-to test molecules, right? Because adding bromine can be really useful. This is literally how you make bromobenzene that we used to make our Grignard reagent last week or 2 days ago. Right, so in order for this to happen, if we were just looking at hallucination, the first bromine we added is going to act as an electrophile. Because if you remember this mechanism, we brought in Br2 too. This is not a benzene ring, this is just an alkene. And we basically said, okay, well, if you've got a bromine, if you've got Br2, one of those bromines can take a pair of electrons, and the other one thing is missing a pair of electrons, and it basically bonds on to the electrons from the alkene, from the pi bonds. We made this bromonium ion, and then we had our nucleophile come in from the other side. This is similar to what we're going to see. This is still bromine acting as an electrophile. The problem is bromine just Br2 on its own is not a strong enough electrophile to do this if it's benzene. So we need to make a stronger electrophile. And that's what the iron does. Right? And so back when we first learned what acids were, we defined them. We talked about Lewis acids. And back in Gen Chem, you probably heard, here's a definition of an acid called a Lewis acid. We're not going to use this again until we get to OChem. This is it finally showing up again.
Actually,
Right, so it's a Lewis acid, and it can be just iron, or it can you can also add iron tribromide, iron-free bromide is used as well. So we're showing it with iron-free bromide, but iron metal does the same thing.
so that's what we're showing.
That's what this looks like. That because that's this molecule.
Okay.
If you do this, the iron-free has empty spot in its d orbital that it can accept more electrons. Actually, I don't think it has to use the d orbital. Think about it. Yeah, it's got an empty spot in its p orbital that allows it to do this. Basically, what you get is you get this weird cross-shaped structure. It's not actually a cross-shaped structure, because that's going to be tetrahedral now. But where we get bromine single bound to a bromine single bound to an iron, that gives the iron too many electrons. The iron gets a negative charge from this. And that bromine that's in the middle that has two bonds now has too many bonds. It doesn't have enough electrons, so it gives it a positive charge. That's going to make it want to pull the electrons closer to itself. So by doing this, this last bromine, the one that's not directly attached to the iron, is very loosely attached, and it doesn't have priority when it comes to pulling on these electrons. So even though this is a bromine to bromine single bond, which we would expect it to be pure covalent and evenly shared electrons, the fact that the iron's there and this bromine has a positive charge means this bromine is actually missing electrons. It's donating some of the electron density to this bromine to account for that positive charge. Which makes this bromine our electrophile. So it's going to be very similar to what we saw with the addition reaction, except even more so. Now it's even more pulling the electrons towards one side of that bromine bond. which makes it act like this. We're never actually going to see bromine with a plus charge, but it can behave that way. The same way that with our Grignard reaction, when we had our Grignard reagent, if we had CH3 MgBr as a Grignard reagent, we could basically treat that like it was CH3 with a negative charge, even though it was really still attached to the magnesium. We could draw a mechanism this way, right?
Yeah.
So that's basically what we're going to do with these electrophiles. They're in these weird, unstable Lewis base acid complexes, but they're going to be able to react like this. So if we have Br plus, a strong electrophile, and we have a benzene ring, what's going to be attracted to what here?
Extra electron density in the, like, on the carbon stacks are attached to the bonds.
Right.
So they're like kind of attraction.
Correct. We have extra electron density, so we're gonna get something like that. Which is not great from a stability point of view, because we just broke up the aromaticity. There was already a hydrogen here and a hydrogen here. One of those carbons becomes tetrahedral. And the other one now is missing a pair of electrons.
Yes. So something negative comes in and taps the positive.
That's one approach. So let's say we just had hydroxide around. We could do that. We're not going to reform the benzene ring then. We wound up breaking the benzene ring if we did that. What if instead of attacking there, we did a proton transfer? This is a lot like the second step of an elimination reaction. When you think about an elimination reaction, we had our leaving group had to be kind of pushed out sometimes, right? And when it left a pair of electrons that then could make a pi bond.
Yeah.
So if we grab this H plus, it's not really an H plus right now, it's part of the carbon hydrogen bonds. But those electrons that are part of the carbon hydrogen bonds can move over that plus. So basically we did a swap of the electrons. So the electrons that were part of the carbon hydrogen single bonds then turn into the electrons that are back as being part of the aromatic ring.
And it goes to the plus, or it makes another double bond.
It's both. It's gonna go towards the plus, which creates another double bond.
And if it just moves in the plus.
So that makes our final product then bromobenzene.
It doesn't seem too bad.
It's not. It's different than what we've seen before. We're not used to dealing with electrophiles.
Yeah.
But other than that, it kind of makes sense with our rules for pi bonds and charges and everything. And what makes this possible, because it doesn't seem like a good idea to break our aromaticity, which is why we wind up making it back in the end anyway.
But what makes this possible is that this piece here has a bunch of resonance still, right?
Yeah.
There's 3 resonance structures. I'm gonna erase these. Actually, I'm gonna erase this whole thing because I have it all drawn out on the next slide. Having all those resonance structures makes it actually a relatively stable intermediate.
What do you do with the product?
This is how you make them. Yes. You're taking this, well, really, you're taking this bromine and having it attack a bunch of electron density.
That we were studying, but the start of the thing to think, how it's like, no, you don't.
Yeah, this is the first step, like you said. The first step in all of these mechanisms, the reason that electrophilic aromatic substitution is all considered one mechanism is because the first step is always make an electrophile. And then the second step is always your electrophile attaches to a benzene ring. All right, so here it is drawn out a little bit neater.
This makes it look worse.
It's the exact same thing we just drew.
But it showed
All the resonance structures. So all of these resonance structures collectively, this whole thing, because all of these are happening simultaneously, right? This whole thing is called a sigma complex. Because we broke a pi bond to make a new sigma bond, we have an extra sigma bond compared to what a benzene should have. And then but your next step is always kick off a hydrogen with your hydrogen is going to get attached to something. So in this case, it's just one of those bromines. We use hydroxide in our first example, just because that's our go-to for a base versus a nucleophile. In this case, because we made this FeBr4 or anion, we've got something around that can act as a base. So basically, you're just going to get the bromine, the other bromine that was part of this Br2 at the beginning, comes back off and turns into an HBr, and we get our Br3 back as a product. So we've regenerated our catalyst. And so we're almost always going to show it this way, not just as iron. Because if you do it just as iron, the same thing happens, but you have to use 3 times as much bromine. Because the first step is always your iron reacts with the bromine to make this. And then once you make your iron through bromide, any bromine that's left can go through this process. So we usually just going to write it. And aluminum is going to look identical, except instead of iron, it's going to be aluminum chloride. So AlCl3. All right, so first, and I guess step 0, the way they're counting this in the way it's written out, step 0 is make your nucleophile, or your electrophile, excuse me. Then your electrophile attaches to the benzene ring, you make your sigma complex, and lastly, you deprotonate it and you make the benzene again. Technically, this can happen to any aromatic. So you can do this with naphthalene, you can do this with furan, which is that one that looks like this. The specifics are going to be a little bit different, but it'll do the same basic reaction because anything aromatic can make a sigma complex like this. And so if you had something like this or something like naphthalene, the other way. If you have naphthalene or furan or anything else similar to this, then there's different carbon positions, and so there's more details to it. But it'll still do the same thing. You can still make bromonaphthalene using the same mechanism. You can still make bromofuran using the same mechanism. It's just where do you put the bromine?
gets a little bit tricky. And it's beyond what we're gonna spend most of our time on in this course, so we're gonna focus on benzene as our default aromatic, because it's the most common. So this goes back to your question about why don't we get the addition product? Why doesn't our nucleophile attach to the positive charge? Basically because it's not thermodynamically stable. We don't get to remake the benzene ring by doing that. So we're not gonna see that product really.
Yeah.
It actually probably is slightly lower in energy for the transition state than making our substitution product. But they're close. Obviously this isn't scale, this is all qualitative. They're close to the same, but this one's so much more favored by thermodynamics.
Yeah.
That we're basically only going to see the substitution products. Should we do practice?
Yeah.
Like I mentioned, identical mechanism, except instead of iron, it's aluminum. Instead of bromine, it's chlorine. So give this a go, and then I'll work through it, and then we'll take a break.
Did you do us the same thing? You're waiting for her.
While drawing all three of the resonance structures for the sigma complex is not strictly necessary to get to the right product, it's good practice because it's going to explain Tuesday's lecture a lot better if we can draw those resonance structures.
Okay. So we should do like a parentheses.
Yeah. Little brackets.
Yeah. We want to just. Well, I don't have to redraw that way. Okay. Now I need to point. That's probably the. Bring it down, bring it. This. Bring. This. Because it says, yeah, but we're gonna show that it's looking around a bit. Maybe it should. Down. Yeah. Yeah. We did that for them. And then let's move it around the ring. Long ways. Like, oh, counterclockwise. This is show. It's the same thing.
Get started.
We're kind of stuck in the brackets.
Okay. Let me get caught up then. So it doesn't matter which pi bonds you pick
Okay.
in this part because it's going to be that regardless. And since all of these carbons are identical, pick the one featured closest to it. It's the way you turn it. So then our sigma complex then looks like, I started with this color, but I don't like this color. Straight back. The purple just shows up the best.
It does. Calculate the purple ones too.
So for the sake of being consistent, even though all these carbons are the same, I'm going to try and keep everything in the same spot. So we had a hydrogen here already. Now we added a chlorine. And in doing so, we created a positive charge there. So there's the one of our resonance structures for our sigma complex. So our rules for resonance structures is no sigma bonds can move. And you can't move electrons towards a full octet. But we can do that. Which leaves a positive charge here. Which means our last one is going to look like this. And it doesn't matter which one you can pick either of the two on the ends for our next step.
Okay.
So the other way that you can think about this that uses terminology that we should be getting used to is
the positive charge in our sigma complex is gonna go in the ortho and para positions on that ring. Right, ortho means adjacent, para means opposite. So pick one of the ones where the positive charge is ortho. Because then our next step is just, we have that AlCl3 or AlCl4 ion floating around. So we're just going to bring those electrons over and grab that. These electrons move over to the positive charge because the positive charge is empty spot in the valence. So we get HCl, AlCl3 again, and chlorobenzene. This whole thing, all three of these together, is considered the sigma complex because they're all happening simultaneously. It's not one of the resonance structures, all of the resonance structures collectively.
Yeah. Showing the results and that, so. For the red arrow that you have there first is how we did there. But then this arrow that's coming in, it's like a different, like you could redraw this, it's the triple.
So if you've already drawn these arrows of your resonance structures, then you might want to just use this one.
Okay.
Because this one doesn't have any any arrows drawn on it. But it doesn't really matter because these are really equivalent.
Yeah.
That's all there is to this whole lecture.
Is it?
Well, kind of. There's still 4 more reactions we haven't looked at yet, but the only thing different about them is we have to make different electrophiles. So the rest of this lecture is just, here's 4 more ways we can make different electrophiles, but they all do the same thing.
So step 2 is the same, but step 1 is good.
Exactly. They're still gonna make the same sigma complex, just with something that's not chlorine or bromine, and they're still gonna do that same last step where you pull a hydrogen off and remake benzene. So let's take a break.
Okay.
Let's come back at 5 after. All right. Let's go back. Like I said, the rest of this is going to be more of the same. So this is just the cleaned up version of, or this is the general form. As soon as we have our electrophile, they always go through the same steps, just like the 2 that we already did. Right? So the only thing different at this point is how do we make the electrophile and what is it? So our first one is you can add a sulfate group or a sulfonyl group to this, making an SO3H added, so we make sulfonic benzoyl. I don't know what the name is, doesn't matter. We don't name the sulfur stuff that much. And you can tell that these reactions, we can get decent yield, but they're still not, I mean, I guess 95% is good yield. But it still takes a lot to get us there because we have to do this making fuming sulfuric acid. Fuming basically means that it's a way to get a more concentrated version of H2SO4 than you can get just by having concentrated H2SO4. Concentrated H2SO4 has a molarity, I want to say it's like 15 molar, maybe 19 molar. We can actually get it higher concentration, get it stronger by bubbling SO3 gas into the concentrated H2SO4.
Okay.
And so they call it fuming because it's basically it's got this gas dissolved in it, and it makes it even more reactive. So basically, the SO3 is actually going to be the nucleophile in this case. So sulfur trioxide has this a little bit different of a Lewis dot structure. It's actually one of our favorites to ask about on a Gen Chem test because you can draw it, the Lewis dot structure, as like this as well. But it's not as accurate as doing it like this because that gets our formal charges all to 0. And we can do that because sulfur has a d orbital. We can't do that with a nitrogen. So like for nitrate, nitrate's going to look like this because you can't make that the 6 bonds to that middle part. So what we're going to see here, and this is a good one to ask about on Gen Chem, partly because, and actually it's even better if we ask about it on intro, Chem 100, because if they draw, we don't teach them about what happens when you break the octet rule, Chem 100, so if they give me that structure, I know they cheat. So same basic idea here. Our SO3 is the nucleophile. So you have to know that fuming H2SO4 means it's got SO3 in it.
Okay.
And we're just going to use SO3. So there's no mechanism step to draw the electrophile in this case.
It has SO3 in it.
Exactly. So that's what makes it fuming. It's the fact that we take this gas and we dissolve it into the H2SO4. It's a little bit like how if you dissolve CO2 in water, you get carbonic acid. You get a mixture of both carbonic acid and CO2. If you dissolve SO3 in water, you get sulfuric acid, but you still have some dissolved too. So if you saturate the H2SO4 with SO3, you get fuming sulfuric. This is also the impurity that causes acid rain.
Oh. So
coal burning power plants that don't remove sulfur effectively from coal before they burn it, they make SO3 the byproduct, which when this goes into the clouds, it dissolves in water and makes H2SO4. So it makes the sulfuric acid. So really, really analogous to dissolving CO2 in water to make carbonic acid, except more extreme because we're making sulfuric acid.
Have we had instances of acid rain?
Not much on the West Coast. They're really common. It was really common in basically going back to the 50s and forward until about the 2000s in the Northeast, where they have more coal burning power plants.
Did they not know that that's why?
There's always a lag between when we figure out that something's happening. So they first discovered acid rain probably in like the 60s or 70s, but government regulation and forcing these power plants to actually clean stuff up and take care of it and remove that took a couple decades behind that.
Like
Basically,
fields are dying.
Yeah, basically. Like ponds and streams were basically completely dying
Like they were becoming completely devoid of plant and fish life.
For human skin?
No. For the most part, if you live really close to one of these power plants, then maybe you might notice some skin irritation. It wouldn't give you like chemical burns, but you would definitely have like some issues with your skin if you had sensitive skin, especially. It's one of the things have you taken an environmental science class before? So one of the big things in the 60s that was kind of the result of the hippie movement in some respects, environmentalism first getting started was the formation of the EPA. The EPA, Environmental Protection Agency, didn't exist until the 60s.
Oh,
So up until that point,
things were going unchecked.
basically. And it took a bunch of stuff like the Aaron Brockovich trial that we talked about, like chromium leaching into the groundwater. That was in the 90s, but before that, there was a similar incident in the Northeast in New York, in upstate New York near Lake Erie, where they found that one of the big chemical suppliers, I don't remember if it was DuPont or Dow, but I'm pretty sure it was one of them, was basically any chemical waste they couldn't use, they would just put it in that steel drum and bury it.
Oh.
And chemical waste eats through steel drums eventually,
Yeah.
and it was leaching into groundwater, and they had this huge issue. And then this is one of the few things, I want to say it was Nixon, one of the few positive things that Nixon did was forming the EPA as a result of that. And so then they started cracking down on acid rain and stuff like that as well. It's really interesting. If you look at, we actually have one of the first things that the EPA did was establish what they call Superfund, the Superfund, which is basically anybody who makes chemical waste is required to pay into this government controlled fund that gets used to clean up the messes.
Yeah.
So if they weren't cleaning up after themselves, they still had a way to, the lawyers would go back and say, hey, no, you owe this much money to the Superfund. Then a Superfund would go clean it up. We actually have a Superfund cleanup site here in South Lake Tahoe. Do you know where the old dump is? You know, Spray Road. There's like those mountain biking trails that are on the south side of Pioneer.
Okay.
So like all that undeveloped land
Yeah.
on the south side of Pioneer used to be the old dump for the town.
Okay.
And so it's full of a bunch of lead-based paints and things like that from the 50s, 60s, 70s. And so they had to go through and do a reclamation project to remove a lot of that and make sure it was properly contained. There's still some roads back that they still have to check on it every so often. We don't use it as a dump anymore, obviously.
What are they checking for? Just to make sure.
Just to make sure that the containment is holding so that we're not leaching lead into the groundwater. There's probably some other stuff besides the lead, but lead-based paint was a big one. Old dumps
Yeah.
in areas where the groundwater all goes to the same place have issues with the lead-based paints.
Sense. Just use all the lead-based paint. That's what you just.
That's what you use. Lead-based paints work really well for houses inside and out. So before you had organic-based paints, lead-based paints made really good colors. They had really good coverage. They coated things well. They were easy to use. They just, had lead in them.
You just put lead in makeup.
Yep.
That's part of the reason they think. I think the person female was that she it was like a liquid, so she put it on and then she get chemical burns from it.
This is the one that Margot Robbie played in the recent biopic, right? Yeah.
And so she would put more on to cover her burns and blemishes that she was getting from it. And so they were she has her a thick layer of just lead on her face, so she's inhaling it all the time. And I realize that's what this caused.
Right.
Probably.
So that's also the most likely cause of death for Napoleon Bonaparte.
Oh, okay.
Because they used all these lead-based paints in Europe where they were relatively stable. But then the Europeans, when they colonized tropical areas, brought the lead-based paints with them. And lead-based paint does not hold up as well in tropical climates because of the higher humidity and the higher temperature. And so when Napoleon was exiled to the second time he was exiled to Saint Helena, I think,
The island,
the island that was in equatorial Africa.
yeah,
And so basically he got sick, so he spent time in his room. The more time he spent in his room, the more sick he got because it was actually the paintings on the walls. And it also makes you, unhinged.
yeah.
So that accounts for, as they got older, they got progressively crazier. All right, so we've spent this whole time talking about other things because we've already talked about this kind. So now we've talked about what
Yeah.
sulfuric acid is. We don't really need to spend a ton of time here. The one thing that's unique about this mechanism is we just have one extra proton transfer at the end because our final product has an oxygen that needs to be protonated. So our first step, where our pi bond attacks the sulfur, creates an oxygen with a negative charge to make room for the new bond. And so then at the very end, we just do one more proton transfer. So we're not ending up with something with a negative charge.
Is it always gonna be H3? For the,
Just because we made an H3O here.
oh,
If you've got sulfuric acid, you've got water around. So water is actually the strongest base that we have in this situation. So the water will actually grab the H plus and make a hydronium. And then so basically effectively what we're doing is we're shifting the H plus from being attached to the benzene ring, being attached to the oxygen. We're pulling the hydrogen off to make room for the sulfur and then moving it over.
why are these like all equal in these?
Because this is a reversible process. You put it in the right condition, you get everything to go backward. I want to say that the last one was not. Yeah. I don't think, these ones are less reversible because when you generate the electrophile has to get used.
God.
And if you can do this one, adding a nitro group is even easier. Well, it's just as easy. There's no such thing as fuming nitric acid, but we can effectively do the same thing because sulfuric acid is such a strong base, or such a strong acid, it can force nitric acid to act as base. Which is why. Okay, so this one does have a generate your electrophile step. And so generating the electrophile in this case is basically your sulfuric acid protonates your nitric acid. And then we get this weird intermediate that looks like H2NO3 with a plus charge. And that immediately is just going to kick off a water molecule to make this NO2 with a positive charge. And so we call that NO2 with a positive charge. It's not nitrogen dioxide because that has a charge, so we call it nitronium.
Okay.
The Lewis dot structure is basically just CO2 with the nitrogen instead of a carbon.
I'm assuming this is a little bit step one. Yeah, this is step one, but then step two is gonna be the same. So
Exactly. Now we have our electrophile, it attaches to the benzene ring to make a sigma complex. So let's do another practice. We're gonna be really good at drawing this one by the end.
this specific one,
Well, because all of them are the same. So you have the electrophile, right?
but step one is all different.
So starting from the nitronium, draw the rest of the methods.
Oh, okay. Wait. So step one, are we expected to have none like no, or they can? Do we always show it?
But I'm gonna give you a sheet of notes.
Yeah.
Like I said, we're gonna practice these enough times, the rest of the mechanism is gonna be really easy.
Yeah. Is that negative H2O or?
No, this minus HO means you just lost the water.
Oh, okay.
In a biology textbook, a lot of times you'll see it drawn like this.
Yeah.
We're looking by Karen.
Yeah. It goes to the top.
Another one though.
In this step?
Because nitrogen can't have more than 8 electrons, right? You got
I like that you can tell them my hand movement, so I'm fine.
been doing this for a while.
We lose H2O because that's what we got from the reaction of
Or just because if we're using nitric acid, sulfuric acid is also water. So another fun fact. The combination of nitric acid and sulfuric acid does have its own name. If you take concentrated nitric acid and concentrated sulfuric acid and you mix them together, you get what's called aqua regia. Which is Latin for king water.
Okay,
Basically, they called it that because it'll dissolve almost anything. So I don't even know if you can buy aqua regia on its own. Because it's almost as destructive as hydrochloric acid. It'll basically, it'll dissolve rock. You take a totally insoluble substance, you can get it to dissolve in aqua regia, including gold.
wow,
So
So-
most acids you can use to clean gold because
Yeah.
they'll dissolve everything but the gold. Aqua regia will actually dissolve the gold.
what, like you can't put it in a,
You can put it in plastic actually.
what?
Plastic holds up better than glass for some of these strong acids like hydrochloric acid and aqua regia.
That's so strange.
It is. Did you watch Breaking Bad?
I know everyone tells me to watch it.
There's a whole thing in the first season where they have a dead body they need to get rid of. And so their solution is we're just going to dissolve it in hydrochloric acid. And the chemist says, go get this specific type of plastic bin from Home Depot. Because it won't, he doesn't say because it won't dissolve in
Yeah.
hydrochloric acid. And the accomplice says, I've got a perfectly good bathtub upstairs. I'm just going to put him in the bathtub. And it eats through the entire bathtub. And then you have this like soggy, acidic dead body that
Great.
falls through the ceiling at one point. But yeah, that is accurate. You can put it in certain plastics will hold up to it, but glass will usually be okay.
Yeah,
But you barely ever buy this. Because they're identical, they're equivalent. Fun story about aqua regia. In World War II, when most of the Nobel Prize winning scientists lived in Europe, when the Nazis started invading neighboring countries.
Yeah.
And so there was the Nobel Prize winning chemist, can't remember who it was off the top of my head right now, who was living in Denmark. He was Danish. And so when the Nazis invaded Denmark, he was also Jewish. So he had to flee when the Nazis invaded, and he didn't have time to go to his office and get his Nobel Prize. And so the Nobel Prize, the medals are made out of solid pure gold.
yeah,
So his colleagues that were not Jewish, that were staying there, they took his Nobel Prize and they dissolved it in aqua regia, and they labeled it and they put it on the stockroom shelf, and they left it there for the entirety of the war. And so Hitler and the Nazis were not able to take that gold because they were famous for stealing any sort of gold or treasure that they could come across. So to keep it from being stolen, they actually just labeled it and put it on the shelf.
oh my god.
And then after the war was over, and he was able to come back, they took that same bottle and they reprecipitated out the gold by neutralizing the aqua regia, and they recast the same gold atoms back into his Nobel Prize medal again.
That's crazy.
Chemists are nothing if not putting anything to pay. We can't stop you from coming to this country, but you're not going to know what that is. I'll have to look up who that was now because I'm curious. All right. So our mechanism, our final product is just this nitrobenzene now, which is also particularly difficult to work with. Nitro groups on anything organic usually means it's going to be explosive. Do you know what TNT stands for?
No.
So TNT is
Is the F stand for nitro?
yep.
Is the T tri? No, that's
Yeah.
it. Oh, it is.
Trinitrotoluene.
I would be so good at this. Yeah, yeah.
So if you take toluene and you nitrate it 3 times,
with this same reaction, you get trinitrotoluene. You take that and you soak it into sawdust, you get dynamite.
And you set it on fire and that's how it blows up?
This is unstable enough that if you drop it, it might explode. So we don't use that version of dynamite anymore. We use a slightly more stabilized version. It's still TNT, but it's more shock resistant. But basically, yeah, if you just touch a spark to that.
So like, what is the explosion? And is it breaking apart?
Basically, you wind up making a whole bunch of nitrogen gas and oxygen gas and burning all this stuff all at the same time.
Okay.
And so basically, and when you generate a lot of a very exothermic reaction that also produces a whole lot of gas at the same time, that's the definition of an explosion, basically.
Because then it burns the gas too. That's like.
If you make nitrogen gas won't burn, but you'll burn the carbons that are left because you're also generating oxygen to some extent. But it's more about the fact that it's super exothermic and you're making a bunch of gas molecules. Less about the combustion. But that one comes back because we're going to talk about what we do when we do these reactions multiple times in a row next lecture. All right, so we're up to 4 now. We got bromine, chlorine, an SO3 group, and an NO2 group. The last 2 are both named after the same 2 chemists, Friedel and Crafts. Friedel and Crafts were the ones who came up with this mechanism. If you take a chloroalkene and expose it to aluminum trichloride, same Lewis acid that we saw before, we can get something really similar. Instead of, so when we used AlCl3 it was with chlorine gas, right? So we made something that looks like this. Like it's a positive charge there and a negative charge there. This is going to do the exact same thing, except it's not 2 chlorines attached to each other, it's a carbon attached to a chlorine. So we just have an R group. That's still, so this is basically just a way to turn a carbon into an electrophile. So a Grignard reagent turns carbon into a nucleophile. A Friedel-Crafts reaction turns the carbon into an electrophile. Which is useful because carbon's kind of right in the middle in terms of electronegativity, right? That's this. It's just with a generic R group instead of a specific one. Right, so what this does effectively is the way that it won't rearrange to make a carbocation stable enough to react through this process. Technically, any carbocation is an electrophile, but we can't make carbocations that last long enough to react normally. So this intermediate, this weirdness right here, is just stable enough that it won't rearrange and it'll last long enough to react with the benzene ring.
Right. So I like in these we're making the ones in the green box. But then when we do like write out what's the mechanism, do you want us showing like the last step to be with the second step that's coming in to take what it needs?
This is more likely what it's gonna exist as.
Yeah.
And then it's gonna do this step when it actually reacts to the benzene ring, but I'm okay with either going to the green box or starting here for the next step. And in fact, probably this middle step is more accurate, but it's a little bit more complicated to draw.
Yeah.
So your choice.
But if we show like this whole step before it, we would understand like we know the method.
Exactly. And then the last one is basically the same thing, but a slightly more specific version. instead of just being an alkyl chloride, it's an acid chloride. So we effectively, this gives us a way to, it's a carbonyl with positive charge, is gonna be our electrophile in this case. And this one actually has a better yield. So Friedel-Crafts alkylation has pretty poor yield, and we don't want to use it unless really no other option. The acylation, this acylium ion, is more stable and gives us, but more importantly, it gives us better yields. And that's why they both have the same. I believe historically that they figured this one out first. And then realized as they were like, they were only getting yields in the, close to 50% range, 30% range. And then they figured out that if they did it with an acyl group instead of an alkyl group, they got better yields closer to 80 to 90%. So this basically, this is the one that everybody uses. Alkylation still exists, but it's more historical.
Maybe it was Niels Bohr. Oh, who was it?
Yeah, I think that one. That's.
So in this, I take it back, you do see some amount of carbocation rearrangement happening. So with the alkylation, you'll get a mixture of products. The rearrangement doesn't happen quickly because of having that aluminum present, but it does happen enough that you get a mixture of both of these. And even if it does, you don't have a rearrangement happening, my numbers up here say 66% yield. It's about as good as you're going to get. Okay. And it also only reacts if it's an sp3 carbon. If you put a chlorine onto an sp2 carbon, this doesn't work. Okay. So both of these reactions, the Friedel-Crafts reactions, are fairly limited to some extent. But the acylation will give you the better yields and will definitely not rearrange.
Oh, goodness, okay.
And so what makes the acylation a little bit more effective is we get a resonance structure from our electrophile. So our alkylation didn't have that. The only way our alkylation in our electrophile can become more stable is by doing a rearrangement. But we do have two possible resonance structures if the carbon that has the positive charge is attached to the oxygen. So that gives a little bit more stability and stops it from rearranging. So our mechanism will actually look like this. It'll still be pi bond breaks, forms new signal bonds. We do have to make room, depending on which resonance structure you chose to throw it at draw as. Starting from this resonance structure, there's already room on that carbon, so you don't need to show it. We make our sigma complex. We do a proton transfer. It's still the AlCl4 going to act as our base in this case. And we get our acyl product.
So it's like the top is step one and the bottom is step.
Exactly. The top is generating the electrophile, and then the bottom is our regular electrophilic substitution. So it's normal that even though that was the same mechanism 6 times in a row, it's still 6 reactions. So it's normal to feel a little bit your head swimming.
But at the very least, we can do some practice. We'll finish up with this. So with that, we don't have to draw the mechanism. You can draw the mechanisms for all of these if you wanted more practice. But just draw the products
Do
for
we have rules? It's like farmers can, yeah.
next lecture. Because- Well, for now, they're all the carbons are identical. So there's no difference between our carbon anti because all the carbons are identical. As soon as we do something like add a CH3 group here, now all our carbons are not created equal.
Yeah.
And now we have to dive into it deeper, figure out where we're going to put our next substituent. But that's next week's problem. One step at a time.
Why not?
Because they're all the same. And I want you to think about how they're all the same. So if you don't want to go through rewriting the same mechanism 5 times again, the other thing you could do to test your memory on these and to review it a little bit, we draw with an electrophilic like for each of these. Because that's the only thing that's really different about these reactions, right? But we're not going to go over that right now. We'll end a couple minutes early.
Yes, I started to start, like,
Sweet is this quarter is going to feel like it goes really quickly.
next year I was just. Ripped. I was like, okay, I have class, and then I go home. I was like, oh, I have 2 classes, don't go home. But maybe like on my way there, I was like, I don't even have to switch after. I'm like, what? Because I don't have class today. I'm like, no, I have class today. Switch after I look, I drive, like. A tractor tends to be, I have the audiobook version, and I just listen to it while I drive. What else am I gonna do? All I do is drive. Might as well be productive.
True.
So,
I got really into podcasts when I was driving for a while, 5 days. 5 days a week I was teaching in Klein Village, and I was teaching and I was living here. And so it was just long enough a standard podcast episode, maybe 45 minutes. That was when I was really into home brewing, so I just listened to people talk about brewing science for an hour and a half a day. I got really, really good at brewing science.
I mean, it's cool.
It was fun when we first moved here and we didn't have kids.
Yes.
We also didn't have money, and we picked up a taste for nice beer. Living in Colorado, and Boulder has a really good beer scene. And if you know the right places to go, you could get nice beer for like the same price as
Right.
yeah.
So you started making.
So we just started making it because we couldn't afford it, but we liked it.
Making.
Yeah.
It's great.
All right. Don't forget, you have a free food thing today for student workers. Be sure to thank Laura for it. She spearheads that thing.
Thanks, John.
See you soon.